This problem is about developing rate expression for catalytic reaction by Langmuir-Hinshelwood-Hougen-Watson approach. It is also called as LHHW modeling. So the problem one is the rate expression, developing rate expression for catalytic reaction, which is A plus B giving rise to C by a irreversible reaction, irreversible chemical reaction. The effect of diffusive mass transfer may be neglected. And we are asked to consider the following steps, namely adsorption of A and B, surface reaction of adsorbed A and adsorbed B. For the cases, the product C is not adsorbed or product C is adsorbed. There are two cases of problem. Every problem is involving adsorption of A and B, surface reaction of adsorbed A and B. The product C may not be adsorbed or may be adsorbed. This is the two difference. So step B is to be the rate controlling. Otherwise, we are given with the rate controlling step is surface reaction of adsorbed A and adsorbed B. Okay, first let us consider the product C is not adsorbed. So our steps are adsorption of A and B, which is A attaching with a vacant site S to give attached A, or is adsorbed A, and likewise B is attaching with a vacant site S to give adsorbed B. So S is the vacant site, as I already said. So for these two steps which are in equilibrium, otherwise the rate of forward steps and backward steps are equal. So rate of adsorption of A is given as which is the forward rate constant. Forward constant of this adsorption is KAA, or is K adsorption of A. Small a refers to adsorption, capital A refers to component A. So rate of adsorption of A depends on this concentration of A and the active vacant site. This is active vacant site, that is theta V. So there is a forward step, there is a adsorption of A to give adsorbed A. The rate of desorption of A depends on the concentration of adsorbed A. There is the rate constant for the desorption is KDA. D refers to desorption, capital A refers to component A. KDA refers to desorption of component A. There is a desorption rate constant multiplied by theta A refers to the adsorbed A. Likewise, okay, now let us at equilibrium for the adsorption of A. There is adsorption of A equal to desorption of A. So for the adsorption KAA CA theta V, there is a rate of adsorption, and desorption is given by KDA into theta A. So these two steps are equal. The adsorption step is in equilibrium. There is a forward step, there is adsorption, and the reverse, there is a desorption. Both are happening at the same rate. That is what is the equilibrium step. So because of which we have this thing, is KAA CA theta V equal to KDA theta A. We can rearrange to the form of, or we want to get the variable theta A in terms of, so what is called as the KAA by KDA, what is called as the adsorption constant of A, adsorption equilibrium constant of A, multiplied by the CA and theta V. CA refers to the measurable concentration of component A, and theta V is the fraction of vacant site that we need to estimate. Before that, similar to this thing for A, we can also write for B, or is what is written for A, theta A equal to KACA theta V. Similarly for theta B, KBCB theta V. So we know this components only A and B are getting adsorbed. That's what is given here. No, product C is not adsorbed. So the vacant site, which is what is here? Yeah, this theta V is fraction of vacant site, which is equal to 1 minus the occupied fraction. That is, occupied fraction is theta A plus theta B. That is 1 minus of theta A plus theta B is the vacant site available now. So 1 minus of is this the vacant site. This theta A already we know in terms of KACA theta V. So KACA theta V is here, right? No, theta A equal to KSCA theta V. Likewise, theta B equal to KBCB theta V, and substituting them and rearranging, taking this theta V to this side, and from which we have theta V equal to 1 by KACA, 1 by 1 plus KACA plus KBCB. Otherwise, here we have only the components which are all adsorbed. Since we don't have this risk, since component C is not getting adsorbed, there is no term for that. Okay, that should be kept in mind. We already told with the rate controlling step, which is nothing but the adsorbed A plus adsorbed B reacting to give the gaseous C and 2 vacant sites, because this there is also a balance for this vacant site. There are 2 S, so that will be remaining. So since this is the rate limiting step, we can write the rate equation based on this, assuming this step to be a elementary step. So this AS is theta A and BS is theta B, and we are told with this step is a irreversible reaction. So we have minus RA equal to K theta A theta B. So already we have this theta A theta B in terms of theta V, So that theta V also we have an expression. So now we can substitute everything. So otherwise, what is there? Theta A theta B. Everything will be having is Ka Ca theta V, and this is Kb Cb theta V. Since there are 2 Cv, since there are 2 theta V in multiplication, so the theta V square will be there. Theta V square will lead to this denominator term with square. So that is what is appearing here. Now we need to solve for the second case. What is that? The product C is also getting adsorbed. So for C also getting adsorbed, as already we have written these steps, and now the reaction is now A plus AS plus BS giving rise to CS plus S. Earlier what we have written C plus 2S, now it is changing to CS plus S. So S is the vacant site and CS refers to adsorbed C. So what is desorption of C? Desorption of C is this is forward is desorption, reverse this adsorption will also happen, because except the rate limiting step, all the other things are in equilibrium. So this is a equilibrium step, which means forward step of desorption and reverse of adsorption both will occur at the same rate. So already we have this theta A theta B. Now theta C can also be written as similar to this, so which is coming to be K theta C equal to Kc theta Cc theta V. So now we have 1 minus theta, or is theta V is equal to 1 minus of the entire other quantities, which is theta A, theta B, theta C, all are getting adsorbed. So all are having the same kind of relation. So by substituting them, we have this theta V is coming this way. And what is the rate controlling step? Already we have written, no? Or is this the rate controlling step for which the rate is given as adsorbed, or is rate equal to K into adsorbed A and adsorbed B. So already adsorbed A, adsorbed B relation we have. What is that? This theta A, theta B relations are available. Substituting them, and only this theta V is having additional term. Now earlier for C not adsorbed, we don't have that. Now C is also getting adsorbed, so because of that the denominator is having KCCC. Simply you can compare this. Now earlier for C not getting adsorbed, we don't have that term here. So now because of the C getting adsorbed, there is an additional term. Okay, except that the previous expression and this expression are the same. Good. Now let us see another example, which is A giving rise to M plus N, whereas previously what we had A plus B giving rise to C. Now slightly, earlier we had a second order chemical reaction. Now we have a first order chemical reaction, which is A giving rise to M plus N. What do we say it is first order, or is we are considering this step? This is a elementary reaction. For elementary reaction, the rate is now equal to Kca. So that's what I am telling. It's a first order reaction. So what are the steps involved? They are given already. Adsorption of A, or is A is getting adsorbed on the catalyst, active catalyst site, and surface reaction between adsorbed A and adjacent site to produce adsorbed M and adsorbed N. What is happening? All the things are adsorbed. Since this product is having 2 theta, this is theta m and theta n, both will have this is like ms and ns. So to get 2s in the product, in addition to as, we need to also have another s. That is what is given here. Surface reaction between adsorbed A and adjacent site to produce adsorbed m and adsorbed n. The third step is desorption of m and n, so as to get gaseous m and n. So that are also steps. So we are given with the step 2 is rate controlling. The step 2 is nothing but surface reaction between adsorbed A and adjacent site to produce adsorbed m and n. So for these steps, so these are all in equilibrium. So for which we can write easily this forward step is given by adsorption. Adsorption of A is given by Ca and theta v, and desorption of A is given by desorption of A is nothing but As now. So A is given by KdA theta A. Sorry, this is theta A. So theta is the fraction of site covered by adsorbed species of A. That already we know. And for adsorption equilibrium, the rate of forward step, which is adsorption, and rate of reverse step, which is the desorption, all are at the same rate. So Ka, this is adsorption is Ca theta v Ka, and desorption is KdA into theta A, and we can rearrange to get theta A, which is coming as KaCa theta v. And the second step, the irreversible reaction, and we are given with this is the rate controlling step. Adsorbed A acting with another active site to produce adsorbed m and adsorbed n. So since it is irreversible reaction, so for the forward step, for the reaction rate is given by K into this is theta A and this is theta v. So K theta A theta v. So we need to replace this theta A and theta v in terms of measurable quantities. That is a task now. So we already know this step, whereas the adsorbed m and n, they have to desorb to produce the gaseous m and n. So this is the overall reaction to get that this m and n, what is produced from the surface reaction as adsorbed m and adsorbed n, they are to be desorbed. So for product components, we are writing the desorption steps also, and these steps also in equilibrium. So for adsorption or desorption equilibrium, we can easily write this theta m equal to Km Cm theta v. Likewise, theta n equal to Kn Cn theta v. So everywhere theta v is available, we have to replace theta v in terms of the other quantities, known quantities. So theta v equal to 1 minus of theta a theta m plus theta n, because these are all the components getting adsorbed. So Ka Ca theta v, this is Km Cm theta v, and this is Kn Cn theta v. So taking the theta v to the one side, we have theta v equal to 1 by 1 plus Km Ka Km Cm plus Kn Cn. So there is all the terms, they are getting adsorbed, which are all in equilibrium. They are appearing in this nice term. So here we need to substitute this, or we need to what is the equation already we have. So this is the rate controlling step, which is having K theta a theta v. So theta a is already available, which is Ka Ca theta v, and theta v, additional theta v is there. So we will be having Ka Ca theta v square. So theta v is available. So we are substituting that, and we are having theta v square in that. There is this term in the denominator with the square term. So this is a final expression. So we have seen three kind of model. There is three end expression. The very first one, which is about the second order reaction, or is A plus B giving rise to C. The C may be adsorbed or may not be adsorbed. Accordingly, the end expressions are changing. So this final thing, this is C is not adsorbed, or is A plus B giving rise to C. C is not adsorbed here. Here A plus B giving rise to C with C is not adsorbed. So the previous one, there is no term of C in the denominator, there is C is not adsorbed. Here C is also getting adsorbed, because of which we have the C term in the denominator, and the next second example, which is the first is A giving rise to two components. So here we have adsorption and surface reaction. Here the surface reaction is between adsorbed A and a adjacent vacant site to produce adsorbed M and N. So we have theta A and theta S in the forward step will be coming for the rate limiting step, which is this surface reaction step. So surface reaction is having adsorbed A and theta V as the terms in the rate step that we are going to see, or we have seen it also. So desorption of M and N also there along with adsorption of M. So the denominator will have both A, or is all the terms A, M and N all are there in the denominator because all are getting adsorbed, and we have this thing in square because of if A alone is there to give M and N, we won't have the square term, but here we are given with this adsorbed A is also needing for another vacant site, or is theta A and theta V. So theta A will itself will get a theta V, so theta V. So that's why even for first order chemical reaction we have this square in the denominator. Okay, with this we'll stop now. Thank you.